First of all, good morning, everyone. Thank you, everybody, for joining me this early in the morning. I know it's pretty difficult, especially this time of the year, especially in Michigan or it's Canada. I'm really grateful for my advisors and committee members for supporting me, especially for the last 1 month, so that I could have my PhD defense, which was decided on a short time frame. And I know some of you are even in a different time zone altogether to attend my defense. So I'm really grateful for that. So without further ado, I'll start with my presentation. Today I'll talk about non-equilibrium wall-bounded turbulence and associated noise generation, which I've been working on for the last 5 years. So let's start with the motivation. Now, most flows in industrial applications, right, are quite complex. They are non-equilibrium flow in nature. Considering the case of a subsonic Asia fan, right, we have transient unsteady flow effects due to the rotation of the blade. We have acceleration, deacceleration. Then, due to the curvature of the blade, we have streamwise and spanwise non-equilibrium varying pressure gradient. Then we have curvature effects themselves, which directly affect the Reynolds stresses away from the wall. Then we have flow unsteadiness like separations, reattachments, and laminar to turbulent transition, right? So the essential question is that can the current turbulence model can capture this non-equilibrium flow physics, right? Now, in the past decades, researchers have carried out experiments and simple numerical simulations, such as acceleration on a flat plate, right, flow over a bump, and flow with just adverse pressure gradient. And in most of these simplistic cases as well, most of these turbulence models aren't able to capture the non-equilibrium flow physics as shown in all of these flow scenarios, right? So one of the research goal of the research community is to basically uh, come up with better high fidelity turbulence models. And to do that, first we have to understand the flow physics, right? So that is one of the essential objective of my research. Following that, the second part of my thesis is focused on wall pressure statistics beneath these turbulent boundary layer, that how the non-equilibrium flow physics, which I just discussed, affect the variation of wall pressure statistics along the streamwise or spanwise direction. And why it is important? So it's one of the main noise sources for trailing edge noise, such as cooling fans, wind turbines, propellers, automotive fans, and also it has massive usage in vibroacoustics to check pressure fluctuations in a modern weapon system, as well as air and ground transportation for cabin noise. So reiterating my objective here is that first our focus is on flow physics, that is transient accelerations, then pressure gradient effects, curvature effects, and to do that we are using direct numerical simulations, and the main methodology is to generate high fidelity data sets to understand the flow physics using cost efficient means such as small spans and flat plate, which I'll discuss in detail in the future slides. The second part of my thesis, that objective is to leverage this high fidelity physics to develop a generalized wall spectra model, and and the parameters needed to do that should be uh, can be calculated from the RAN simulation, so that they can actually be used for the industrial applications. So these are the main objectives, right? So let's start with the outline. So the first chapter of my thesis was focused on transient flow acceleration. That is how the turbulence responds to the step jump in mass flux, that how the near wall cycle, that is low speed streaks or quasi-streamers vertical structures, are affected by the step jump in mass flux and how they respond. And to do that in a cost efficient way, that is using this small span methodology, which was previously mostly used for equilibrium flows. So how they can be implemented for these non-equilibrium flow accelerations. And for that, we basically focused on checking the unsteady variation of mean and turbulence statistics, higher order TK budgets, 2-point correlations of velocity, and quadrant analysis. And we found that small span is able to capture the overall variation of the flow physics, especially the near wall dynamics. But there is a small delay in the transition stage, which is attributed to lower streak meandering due to missing span-wise scales. So today I'll not talk about this in detail because first because of the time constraint, especially, and second is that because we talked about this in detail during my comprehensive exam, but we can come back to this if the audience and the jury will have questions about it. So the main focus of my today's presentation will be focused on adverse pressure gradient and curvature effects in turbulent boundary layer. That is, we carry out direct numerical simulations on flat plate with matched pressure gradient on an airfoil. And with matched pressure gradient, we basically pinpoint the curvature effects which are present in airfoil, right? And to do it in a cost-efficient manner, which I'll discuss. And for that, I calculated the streamwise variation of mean and turbulent flow statistics, wall pressure statistics, higher order correlations, and we published this work in Physics of Fluids. And the third and final part of this presentation will be focused on wall pressure spectra modeling. That is, first, it will involve the dataset generation, that how we carried out different direct numerical simulations to understand different flow scenarios such as separation or reattachment. Then we, after gathering the data, we tested current empirical wall pressure spectra models. Then new sensitive parameters were discovered, and a generalized wall pressure spectra model were developed. So let's start with one of the main goals today, focused on adverse pressure gradient and curvature effects in turbulent boundary layer. Now, um, uh, when it comes to adverse pressure gradient effects on turbulent boundary layer, there have been several seminal contributions in the past decade. And some of the important effects of main effects of APG on turbulent boundary layer is that as we go along the streamwise direction, with increase in adverse pressure gradient, we have this faster reduction in skin friction. And secondly, we have higher wake effects, that as you keep on increasing APG, when it comes to mean velocity profile, the wake content of the turbulent boundary layer increases, as well as the logarithmic part depletes. And the third is the Reynolds stresses, that with increase in APG, we have higher Reynolds stresses, especially away from the wall. And when it comes to curvature effects, this work, several experiments have been done since the 80s by several researchers in the past. And the main, but most of these experiments were conducted with minimal or zero pressure gradient. That was, they were mostly focused on curvature effects with minimal pressure gradient, right? And they found that with increase in convex curvature, we have faster reduction in skin friction, right? We have increase in the wake profile of the velocity, and especially the Reynolds stresses decreases away from the wall, which is opposite to what happens in APG effects, right? So as I said, that the previous work focused on curvature effects with zero or minimal pressure gradient. So the research gap here is that what will happen when we have both convex curvature and high adverse pressure gradient flow scenarios, both happening at the same time, and how they affect the turbulent boundary layer when both happens at the same time, right? And to check, so we are mostly focusing the curvature strength from low to mild, that is from 0.005 to 0.02, based on this ratio of delta boundary layer thickness with respect to radius of curvature, which I'll talk about detail in a future slides. So, as I said, we want to focus on curvature effects in the presence of adverse pressure gradient. So to do that, we have this direct numerical simulation on an airfoil, right, done by Howe in 2019, and we compare, we run another flat plate simulation with matched pressure gradient as that we have on an airfoil, and with with the pressure gradient matched in both of the cases, we can the differences will help us uncover the curvature effects which are present in airfoil, right? And the second part of it is that if the turbulent boundary layer is very similar in both of the scenarios and the curvature effects are minimal, then can these flat plate simulations can act as a cheaper surrogate instead of running a whole airfoil simulation. So reiterating my methodology here, so we have this uh, uh, airfoil data, that is, if we have this boundary layer data going from leading edge towards trailing edge boundary layer development as done by Howe. Now our focus is on fully developed turbulent boundary layer with pressure gradients, right? So we wanted to skip the laminar boundary layer, laminar turbulent transition, and FPG effects, and we wanted to focus mostly on fully developed turbulent boundary layer with adverse pressure gradient effects, right? So we started our flat plate simulation from at this midcourt location for the airfoil, right? And we matched so starting from midcourt towards the trailing edge, we match the pressure gradient along the streamwise direction along the chord of the blade on a flat plate. So at the end of the day, we have two direct numerical simulations, right, with matched pressure gradient going from midchord to trailing edge part of the airfoil and on a flat plate. And with matched pressure gradient, we basically uncover the curvature effects which are present in airfoil, So that is our one of the main goal. So uh, for our flat plate simulation, we are basically solving the incompressible Navier-Stokes equation, which is both second order accurate in space and time, solved on a staggered grid. For a boundary condition at the inlet, we have rescaling and recycling boundary condition, so that we have fully developed zero pressure gradient turbulent boundary layer at the inlet of the flat plate. On the sides, we have periodic boundary conditions. At the bottom, we have no slip. At the outlet, we have convective boundary conditions, so that for a smooth outflow of turbulent structures at the outlet. And at the top, we have streamwise varying velocity, which help us to impose the adverse pressure gradient as that we have in our airfoil. Now, before comparing the two cases, that is airfoil and flat plate, first we have to make sure that at this particular x naught location, at the midchord of the airfoil, the turbulent boundary statistics between the airfoil and the flat plate are matching or not. So because first we have to match the turbulent statistics at this particular location, then only we can compare the boundary layer development starting from midchord towards the trailing edge, right? So first we compare the single point statistics, that is the mean velocity profile and the streamwise fluctuations and Reynolds stresses. And you see, when we compare, we also compare it with the literature that is done by Spellards at match Reynolds number. And we find that the single point statistics is overall very nice variation for all the cases. Next, we also compare the two-point velocity correlations between flat plate and airfoil, near the wall and away from the wall. An overall comparison between the two cases is very good. And so overall, based on this analysis, we see that at this x naught location, the turbulence statistics are in very good comparison. So we can go on and compare the boundary layer development starting from midchord towards the trailing edge part of the blade, that how the turbulence statistics and the mean velocity profile vary along the streamwise direction along the chord of the blade comparing with that of a flat plate. First, I'm showing here is the variation of displacement thickness, right, along the chord of the blade and along the streamwise direction of the flat plate. And you see that the overall variation, the increase in displacement thickness with APG is captured nicely by the flat plate, except some differences towards the trailing edge part of the blade. Then we also compare the variation of skin friction between airfoil and flat plate. And you see that the overall variation is also again comparing very nicely between the two cases, except there are some differences near the midchord and towards the trailing edge, which is due to the curvature effects which are present in airfoil, because both curvature effects and APG leads to decrease in skin friction, and for that reason, these curvature effects leads to faster reduction in skin friction, especially for the airfoil case. Next, we compare the uh, curvature strength and the pressure gradient strength varying along the streamwise direction. So for airfoil, when it comes to curvature strength, it's basically the ratio of boundary layer thickness at a local position normalized by the radius of curvature of the blade. And higher this ratio is, higher is the curvature effects. And as we go along the chord of the blade, along the streamwise direction, right, with with increased APG, the delta, the boundary layer thickness of the boundary layer thickness of the turbulent boundary layer increases, which leads to increased curvature effects, actually, and that is what is reflected for the airfoil. Next, we basically compare the pressure gradient, which is calculated using the Clauser parameter, which is nothing but a ratio of pressure gradient with respect to wall shear stress. And we find that as you go along the streamwise direction, we have a good overall collapse between the two cases, except towards the end, in which we have stronger APG effects for the airfoil. That is because of indirect effect of a curvature effect because of faster reduction in wall shear stress, which we discussed in the previous slide, reflected in skin friction. Next, we compare the mean velocity profile at different streamwise locations, going from mid-chord towards the trailing edge part of the blade along the streamwise direction. So we calculated a different streamwise location between flat plate and airfoil, right, with matched pressure gradient as seen in the other two plots. So you see that with increase in APG, we have increase in the wake, which is reflected both in flat plate and airfoil, right? And the overall variation and the trend is varying very nicely between the two cases. Second, we have the variation of stream-wise fluctuations, that how they vary with increase in APG. So as expected, with increase in adverse pressure gradient effects, we have higher stream-wise fluctuations because of the energized turbulent structures away from the wall with APG. And the variation and the trend is very nicely captured between flat plate and airfoil. with not major difference between the two cases. Third, we compare the Reynolds shear stress development similarly along the streamwise direction, and the overall variation and comparison is very similar, except there are some differences. First is near the midcord. You see that at this particular location, at just towards the start, we have low adverse pressure gradient effects, right? Because Clauser parameter is pretty minimal; it's less than 1. And you see that at this particular location, flat plate has actually higher Reynolds stresses away from the wall as compared to airfoil, and that is because curvature effects try to reduce the Reynolds stresses away from the wall, and there is a kind of fight between curvature and APG strength at this particular location, and that's why there is a slower increase in Reynolds stresses at this particular location. But overall, we have a good variation between the two cases. And secondly, as we go towards the trailing edge part of the blade, airfoil actually has higher Reynolds stresses as compared to flat plate, and it is because of the two reasons. First, of the lower Reynolds lower wall shear stress for the airfoil case due to increased curvature effects, and also this curvature effects basically indirectly has a direct effect on Clauser parameter, which actually increases the APG effects indirectly, and that's why we have increased Reynolds stresses for airfoil at this particular location. But overall variation between the two cases is very same. Next, we basically compare the wall pressure statistics, right? So if you take the Fourier transform of the wall pressure fluctuations and multiply with conjugate to get the power spectral density of the wall pressure fluctuations and um, and plot it against frequency. So so first we see at this at the inlet location, that is at the start of the simulations, you see that the overall variation between the two cases between airfoil and flat plate is comparing nicely both at low frequency, mid range frequency, and high frequency. But when we go towards a higher location, that is x by 3 at x bar theta equal to 300, that is towards trailing edge, you see that at the low frequency and mid range frequency, we have a good overall collapse, except there are some differences at the high frequency that could be either due to the curvature effects or trailing edge effects, or because for the airfoil we had compressible flow simulations, and for the flat plate we had incompressible, and that could be one of the other reason. But overall variation between the statistics, wall pressure statistics, power spectral density is comparing very nicely. Next, we compare the span-wise coherence of the wall pressure fluctuations, that how the wall pressure fluctuations are spread around the span direction, that is along this direction, and with respect to the frequency. So at this particular location, that is at the inlet, you see that for both airfoil and flat plate, it's mostly concentrated at the center, right? There is not much spread around the span, right? And it is reflected both comparing nicely between both airfoil and flat plate. But and with increased adverse pressure gradient, like this towards the trailing edge, we have increase in the span-wise coherence between airfoil and flat plate, and it's the magnitude and overall trend is very similar between the two cases. So all in all, we can say that the effect of wall that in the presence of curvature in the that the effects of wall curvature in the presence of APG does quantitatively modify the boundary layer development at some streamwise locations, but all in all, adverse pressure gradient effects dominate curvature effects for the whole streamwise direction, and we can say that the boundary layer development is not significantly modified by the curvature. So we can use these flat plate simulations as a low cost surrogate to understand the non-equilibrium flow dynamics on airfoils. Now, the final part of my thesis was focused on understanding the effects of these non-equilibrium flow physics on wall pressure statistics, and then modeling it for equilibrium and non-equilibrium turbulent boundary layers. Now, when it comes to wall pressure statistics, there are basically two major effects which has been discussed in the literature. So if you calculate the power spectrum density of the wall pressure fluctuations, right, and then normalize it using UE, that edge velocity as the boundary layer edge velocity as a velocity scale, wall shear stress as the pressure scale, and delta as the length scale, and plot it against frequency, what is found that it scales by omega square at the low frequency, and then it scales by -1 around at the overlap frequency, and it scales by -5 at the high frequency. And with increase in Reynolds number, it is found that the overlap frequency basically stretches with increase in Reynolds number, as well as the high frequency content increases with increase in Reynolds number. And this is mostly for equilibrium zero pressure gradient turbulent boundary layers. Now, next, when it comes to adverse pressure gradient effects, what has been found that this is pretty common as you go towards the trailing edge part of the blade. So what has been found that the low frequency content of the wall pressure statistics increases and the high frequency content decreases. Now, there have been different strategies to understand to model this the effect of these physics on wall pressure spectra. One of them is Goody's model, who try to model this Reynolds number effect into equilibrium zero pressure gradient turbulent boundary layers, and based on his he used this RT parameter, which is a function of friction Reynolds number and skin friction, and he was able to capture this Reynolds number effect, but it was only applicable to zero pressure gradient turbulent boundary layers. Right, it practically fails for other non-equilibrium flow scenarios. Next, there was this approach by Rosenberg's, in which he tried to capture the APG effects using pressure gradient parameters such as Clauser parameter and Wake parameter, and it worked nicely for APG flows. But there are some issues with it, that it fails at high APG flow scenarios at high Reynolds number. It fails as we go towards separation, and it doesn't work for different flow scenarios such as favorable pressure gradient and reattachments. And and there have been several other models which follow the same ideology, which is done by Rosenberg, but they also have the same issues as the Rosenberg's model. So our focus is to first, as I said, is to develop a generalized wall pressure spectrum model, which for all equilibrium and non-equilibrium flow scenarios, applicable to high load scenarios, favorable pressure gradient, separations, reattachments, right? And it should also work for different Reynolds number range. And most importantly, it should be the model should is dependent upon parameters which is computable from the RAN simulation, so that they can be actually used for industrial flow scenarios. And to do that, first we have to understand the effect of these non-equilibrium flow physics on the wall pressure spectra. And for that, we basically gather data based on direct numerical simulation and experimental data from the literature, encompassing different flow scenarios and low to high Reynolds number. So let's start with the database collection. So we basically, for the direct numerical simulations, in addition to the DNS simulations, which I discussed in the previous slides on flat plane and airfoil, we ran further more simulations. Like we reran the simulations done by Nayan Moen and Wu Pameli, which had flow separation scenarios, so that we can capture the wall pressure spectra at different streamwise locations before separation, within the separation, and after reattachment. And by doing that, we cover a Reynolds number range going from 300 to 2500, which is basically the highest we have seen in the literature for the wall pressure statistics. And the Clauser parameter going from 0 to 200. And we also include different flow scenarios such as flow separation and reattachment, as shown. Now, we didn't want to limit us to low to mid high Reynolds number. So because we want our model to be generalized, so we gathered more data from the literature based by referring to experimental data set in the literature. So that we can cover a Reynolds number range going from 5,000 to 23,000, with Clauser parameter going from -1 to 12. Now let's look at the wall pressure, let's look at the wall pressure statistics, that how these different non-equilibrium flow physics affect the wall pressure fluctuations at the wall, right? So here I'm comparing all the direct numerical simulations data which we have, the flat plate airfoil and the Nayan Moen and Wu family, which we reran along the streamwise direction. So here I'm showing the variation of normalized wall pressure fluctuations, RMS fluctuations, normalized by inner scales, that is wall shear stress, and then normalized by outer scales, that is local maxima of Reynolds stresses. In the first part, what we see that when we normalize by wall shear stress, with increase in adverse pressure gradient, especially going towards separation, With increase in adverse pressure gradient, this scaling basically fails. Why is that? That is because wall shear stress goes to minimal or zero values because with APG, right? And with that reason, this scaling practically fails. It goes to infinity, right? Because it's basically goes to undefined values because the denominator is going towards zero. And still, most of the models use the scaling, right? So that's very clearly suggests that why most of the models fail. And the second, when we use the local maxima of Reynolds stresses, for all the attached boundary layer cases, we have a collapse for all the cases which we have for the DNS cases, right? For the all attached boundary layer cases. But whenever the flow separates, right? Whenever the flow separates, the turbulence structures are away from the wall. The shear layer is basically detached, and for that reason, all the high frequency content is separated, and we mostly have the recirculating fluctuations, and that's why we have this dip in the profile when the flow separates, right? That is reflected both in 9 Moen's and Wu by Emily's case. But all in all, for all the attached boundary layer case, we have a collapse when scaling by local maxima of Reynolds stresses. Next, when we calculate the power spectral density of these wall pressure fluctuations, right, at different streamwise locations, right, for all the DNS experimental data set we have for all the attached boundary layer cases, and then scale it with different scaling, that is using inner scaling that involves friction velocity, right, and viscous length scale, and right, and then mixed scaling that using wall shear stress and delta, right, and then outer scaling, right, we see that for the inner scaling and mixed scaling, the lines are all over the place, right? And for auto scaling, we have an overall collapse. So my main point of the slide is not to like confuse you with all of these lines in a plot, but to make a very important point that the current wall pressure spectra models basically use this inner scaling or mixed scaling, and you see that the lines are all over the place for all the different cases, all of these non-uniform flow scenarios, and that's one of the reasons they fail. So for our generalized wall pressure spectrum model, we will use this outer scaling in which we use local maxima of Reynolds stresses as the pressure scale, delta as the length scale, and the UE, that is the boundary layer edge velocity, as the velocity scale, right? So that is one of the first step of the wall pressure spectrum model development. Now looking deeper into the physics, now, if we segregate this based on Reynolds number, that is low Reynolds number cases with RE theta less than 600, then for RE theta somewhere between 2500 to 5000, and then for high Reynolds number cases, right? When we basically segregate for the low Reynolds number cases, we see that we have an overall collapse between all the cases, right? It's a sort of cell similarity which is reached with this particular scaling for low Reynolds number. For mid to high Reynolds number, you see that with adverse pressure gradient effects, we have the overlap range at the high frequency content basically decreases with increase in adverse pressure gradient, right? So that is one of the effect, and this is similar seen at the high Reynolds number cases as well. So that is one of the important observation which will be helpful for the model development. So next, we compare the different wall pressure spectrum models which we have in the literature, right? The Goody's model, Lee's model, Rosenberg's model, Hu's model, Kamruzaman's model, right? And we test it for different flow scenarios. So in the blue, we have DNS, and all of the lines are different models. And for all of these flow scenarios, you see that as we keep on increasing adverse pressure gradient from 0 to 200, most of the model not only fail, but they are completely unstable. They give undefined values as we go towards high adverse pressure gradient flow scenarios, right? So the essential question is, why do they fail, right? So there are three main reasons why these models fail. One of them is first is they were curve fitted to a small subset of flow scenarios. They were either made for favorable pressure gradient, either made for adverse pressure gradient, either low Reynolds number, right? And for all of these reasons, these models fail. And secondly, they used the wrong pressure scaling, right? They used wall shear stress as a pressure scaling, right? And you see when we do that, the lines are all over the place, right? So that is one of the second reason. And the third, they are dependent upon parameters which are very sensitive to the pressure gradient, right? For example, the Clauser parameter, it's dependent upon wall shear stress, as we have seen before. And with adverse pressure gradient, as wall shear stress goes to minimal values, it practically reaches to infinitely high values, which basically undefined values. And same is the IRT parameter, which is a function of friction Reynolds number and skin friction, which basically doesn't make sense for all of these non-uniform flow scenarios. And as we keep on going towards flow separation, friction velocity goes to zero, and we have minimal or zero values for RT. Because the parameters goes to undefined values, the models themselves goes to undefined values, and that is one of the other third reason that they fail. So what are our proposal is that first, as I said, we encompassed a large number of force flow scenarios with good Reynolds number range and high and different flow scenarios. Then we use the best scaling, that is the local maxima of Reynolds stresses as the pressure scale, velocity UE as the edge velocity, and delta as the boundary layer thickness. And third, we use appropriate parameters which describes the local status of the turbulent boundary layer and its history effects, instead of just depending upon the local strength of pressure gradient on Reynolds number. So so we basically already finished the first 2 points, right? So we wanted to focus on the third point. So we wanted to look for the right parameters, right? So to do that, we went back to the literature. So this work was done by Farabi and Casarella, in which basically he plotted the power spectral density of wall pressure fluctuations, and as we saw before, and he found that when for these cases, when you increase the Reynolds number going from 3300 to 6000, which is a very good Reynolds number range, we have this increase in overlap range, right? And based on his work, he found that the dominant contribution to this increase in overlap range comes from the log region, logarithmic part of the turbulent boundary layer, right? Similarly, Jaiswal recently, based on his experimental measurements at Sherbrooke towards the trailing edge part of the blade, he found that the overlap part, when he calculated the power spectrum density at the trailing edge part of the blade of the wall pressure fluctuations, the overlap, the most of the contribution in the overlap range came from the logarithmic region part. Again, the same, similar as done by Farabi and Casarella. So based on this work, we wanted this logarithmic region to be the part of the model which we want to develop. So to do that, it was pretty straightforward. So we have this velocity profile, right? And we can subtract the logarithmic part of it, right, out of it, right? And the point where it basically reaches this plateau, where it goes into wake. So this will give us the wide inner plus log region, which I defined by a symbol, by a variable called YW. So it basically gives us how much is the inner or logarithmic region we have within a turbulent boundary layer, right? So it's the average status of turbulent structures within the logarithmic part of the uh, logarithmic region of the velocity profile. Second, we wanted to capture the average status of the turbulent structures, that is the wake. So to do that, again, we use the velocity profile. We can subtract the log layer, and we can use this Coles parameter, which basically tells us what is the current status of the current strength of the turbulent structures in the wake, right? Basically, the wake contribution at a given stream-wise location, right? And all of these parameters, both of these parameters which just discussed, satisfy all the criteria. It will not reach undefined values. It inherently capture the boundary layer history effects, right? So basically, we don't have DNS simulations, we don't have LES simulations, right? So we only have mean velocity profile, right? If we are solving a RAN simulation, right? So from the mean velocity profile, we basically at a given location, the YW, which is the logarithmic region, gives us the turbulent structure we have in the logarithmic part of the turbulent boundary layer, and the Coles parameter gives us the average status of the turbulent structures in the wake, right? Average status, right? And for that reason, these parameters works very nicely, which we'll discuss in the future slides. Now, as reflected here, we calculated these parameters for the cases. So CUC with the increase in adverse pressure gradient. So these are the DNS and experimental data sets for some of the cases which we have. So as you keep on increasing adverse pressure gradient, the wake content increases, which is reflected by the Coles, and the logarithmic part depletes, right, with APG, right? In FPG, it will be opposite, which we'll see, but it makes the point very clear. Next part, like after deciding on the parameters, we wanted to start with the base model, right? So that we can develop a new model. So we started with Goody's model, which was, as I discussed in the literature part, that it is the best model for zero pressure gradient turbulent boundary layers, right? And one of the main reason one question I had, that it worked accurately for all of these equivalent boundary layer, but my question was why it is working for this equivalent boundary layer, right? So if we basically calculate the Reynolds stresses and normalize with the wall shear stress, the local maxima Reynolds stress is basically practical, very is equivalent to wall shear stress. It's around 0.7 to 1. So it's approximately the same magnitude when it comes to zero pressure gradient turbulent boundary layer. That's why this pressure scaling worked for the Goody's model for these particular zero pressure gradient turbulent boundary layer. And secondly, Goody's model inadvertently captured the effect of log region with friction Reynolds number, right? Because this RT parameter which he used is nothing but a function of friction Reynolds number, right? And for zero pressure gradient turbulent boundary layers, the increase in RA tau is proportionately reflected in the increase in log region, but that is not true for other non-Euclidean flow scenarios. But for this particular data set, it works, and that's why this model very works for this particular special case, that is zero pressure gradient equilibrium turbulent boundary layers. So essentially, Goody's model was inherently an incomplete model. So that's why we started with Goody's model as a base, right? And we developed a new model. So instead of using wall shear stress in the Goody's model, we replaced it with the local maximum Reynolds stresses, right? And for ZPG cases, they are very similar, right? It's a special case, but that is one thing we did. Second, to basically to check the strength of the outer layer structures, we use Coles parameter, right? And the third is basically instead of using RT, which is basically a Reynolds number parameter, we replace it with YW, which directly calculates the log region from the velocity profile, right? And by doing that, you see that we tested it for different flow scenarios for a low to high Reynolds number going from 0 to 200. So I'm showing only some of the cases here. So the blue is DNS and the red is the new model, and other cases are different models. So you see for all of the cases, the red is basically collapsing well with the DNS case, and it's varying quite nicely, and also it's very stable even when we go towards separation. And one of the reasons is it is not dependent on parameters which goes undefined values. Now the question is, so I'm just putting forward the main idea again here. So as you see that as we keep on as with adverse pressure gradient flow scenarios, the log region is depleted, and that is reflected in the decrease in the overlap range directly, right? And the increase of the outer layer structures with respect to log region varies the slope, right? So this increase in velocity profile is reflected in the decrease in the wall pressure statistics. So how the logarithm depletes is reflected in the depletion of the overlap range. So that's the main idea which we have right now. That's how they are correlated. Next, we tested the new model against favorable pressure gradient case scenarios, right? And FPG effects are basically opposite to that APG. APG leads to depletion of log layer. FPG leads to basically increase in the logarithmic part. And with the same ideology, so basically the ideology is same, right? And so the new model easily able to handle the FPG, right? So the increased wake and the decreased wake and the increased logarithmic part is easily handled, and you see the new model gives very nice prediction for these FPG flow scenarios. Next, we went to the flow separation. Flow separation was actually pretty straightforward. So we calculated the wall pressure status within the separation when the flow is separated for both Nyan Moens and Wu Pameli's case for the DNS data set we have for different Reynolds number ranges. And you see that for all of these cases, because the flow is detached and mostly it's the low frequency content which is left, and the overall profile of all of these cases is very similar, right? It's sort of cell similarity for the chosen scaling we have, even though we have some differences here, right? But overall the variation is very same. So we added this extra feature into the model that whenever the skin friction goes negative, right, whenever the flow is separated, basically, the model will give you this variation, which works very nicely for all the cases, right? And finally, we focused on flow retachment. So flow retachment is actually a very complicated non-recurrent flow scenarios, right? Because when the flow reattaches, right, the log layer is not formed yet, right? It's kind of an opposite of APG in which the log layer tries to develop along the streamwise direction. It tries to go towards the equilibrium turbulent boundary layer, right? So if you calculate the velocity profile and subtract the logarithmic region out of it, you see that starting from this small dash, which is initially just at the reattachment, and as you go along the streamwise direction, we have this increase in the logarithmic region, and the wake reduces. And if you also plot kappa b versus b, which is and plot it on the Johans and Naguib's correlations, you see initially there is no logarithmic region shown by these circles, but it goes towards the logarithmic region as we go along the streamwise direction. And still our model is able to capture. So initially when there is no logarithmic region, you see as shown by this DNS data, it's directly there is low frequency content, and then there is high frequency, there is no overlap range. But as we go along the streamwise direction, the overlap range begins to form, which is reflected to the logarithmic layer, which is present in the velocity profile as we go along the stream direction. And the new model is very nicely able to capture it. All in all, in conclusion, I could say that we compiled a large DNS and experimental database for wall pressure spectrum modeling. Right, the existing wall pressure spectrum models showed several deficiencies, and for different flow scenarios. So we found the correct parameters, right, which and based on these parameters shows reflect the local status of the turbulence, and it's shown to work for all different non-equilibrium flow scenarios. For the thesis conclusion, I would say that the first chapter focused on the turbulent response to non-equilibrium flow acceleration. That is the change of near wall dynamics, and the how we can use the small spawn methodology to capture the transient flow accelerations. Second was focused on APG and curvature effects. That is the effect of curvature in the presence of high adverse pressure gradient, and how we can use these flat plate simulations as a surrogate tool to capture the non-equilibrium flow dynamics on airfoils. And the third part was focused on wall pressure spectrum modeling for equilibrium and non-equilibrium boundary layers, in which we gathered a high fidelity database, evaluated different models, found their limitations, developed new parameters, and developed a new generalized wall pressure spectrum model based on that. For the future work, we will test this model and improve it for different flow scenarios, such as very high FPGs and APGs at very high Reynolds, very high higher Reynolds number, that are going from 20,000. And the second part, better pressure scaling for separated boundary layers. For example, at these particular locations you see, when the flow is separated, this scaling doesn't work, and that could be one of the major contribution. We can improve the model prediction in these flow scenarios. Third, we can use machine learning approaches so that we can bypass this parameter calculations. Instead of just calculating every time the Coles parameter and wake parameter, we can use these machine learning approaches so that we can bypass this parameter calculation, and directly the variation of wheel velocities clearly can be reflected in the wall pressure spectra. Then the model will be tested against fan flow data, which we have for trailing edge noise prediction. Following that, we can also use it for log layer contribution. To further support the model, we can calculate the log layer contribution to the overlap range based on Wu family's dataset, based on following Jaiswal's work. And finally, as recently shown by Frisch, the rough falls simulations, the wall pressure spectra on the rough falls is the pressure gradient effects on rough falls very similar to the smooth wall, but he tested for low pressure gradient flow scenarios, and we can also apply and improve the model and extend it for flows with roughness. So that could be the final one of the final part. And finally, I'm just showing the work the published work which I've done during my PhD. We published two journal papers, and one is under revision, and the fourth one is under preparation. And I gave several APS talks and at CFD and APS, CFD Canada and APS for that. Thank you, and I can take questions now.